Here we
Oh, yeah, okay. I'm ready.
Okay. So welcome to the second colloquium of the semester. And it's a real pleasure to have this colloquium speaker, Patrick Hennebelle. Patrick is one of the key experts around the world, well-known experts on star formation. He knows everything about star formation from the smaller scales, cloud scales, to impact on galaxies and beyond. He has worked essentially on all aspects of the theory and the foundations of people understanding of star formation, and also the numerical modeling of different aspects of star formation, and also more in general the role of MHD in the formation of clouds and protostellar disks. So even going to scales that are connected to planet formation. And I could spend an hour mentioning all the important contributions in terms of papers, reviews, and so on. And I think he also has a strong link with showing the validity or the non-validity of models by comparing with what we know in the real world with observations, which is not common for all the theories to do so. Patrick started out his career doing a PhD at ENS in Observatorio de Paris. Then he moved after that a postdoc to Cardiff working in a group of Anthony Whitford, when at the time he was working with actually SPH methods, and later moved to work mostly with AMR methods through the collaboration with our former colleague Hennebelle. When in fact, after Cardiff, he came back to France. Became first postdoc at CNRS and then staff astronomer at Observatorio de Paris. And then after that, in 2012, became a permanent researcher at CEA Saclay, where he has been since then. So it's a pleasure to leave the stage to Patrick.
Thank you very much, Lucio. Now, there is a huge challenge to to follow the reputation that you have set. Thank you very much. It's very nice to be here again. I was there like 10 years ago, something like that, also giving a talk, visiting Romain Tessier. Right. So today I'm going to speak about the star formation rate. So of course I would like to acknowledge my young colleagues. Noé, Tine, actually Tine was a student here. She then went and did a postdoc with me for 4 years. She's now in Lyon. And other young and less young people. All right. Okay, so we have the demo effect, of course. It was working, it isn't working, so frozen. Okay, no. Okay, so right. So I like to start with this simple view graph, just to remind, of course, that there is a coherence in the universe and that the large-scale structures and the planets are connected through the interstellar cycle and the, say, baryon physics in general, which is a huge mess. I'm going to be fast in this. I assume most of you knows it. So the message here is that we have to deal here with like 10, 12 orders of magnitude in terms of spatial scales, 20, 25 orders of magnitude in terms of density, 6 orders of magnitude in terms of temperature. So there is a huge sort of direct gravo-turbulence cascade, which leads to the fragmentations in smaller and smaller entities. And then at the scale of the protostar, of the star itself, the stellar feedback started and impact the whole galaxy. So it's a kind of invert cascade. And so we have to deal with the combination of these two aspects. So you have important questions which served as a guideline really for the field development during the last half century, almost 1 century now indeed. So the question that I'm going to address today, the star formation rate that I tentatively place around the molecular cloud scale. This can be, of course, debated, and it's probably a slight oversimplification, but given ideas. The problem of the origin of the stellar initial mass functions, multiplicity and clustering, and of course, formation of disks. So I'm not going to discuss all of that. I'm just going to focus on the star formation rate, but I think it's good to have the full picture in mind, always. All right. So the plan of the talk is the following. I'm going first to discuss the star formation rate from data at large scale and at small scale, and then discuss what numerical simulation found, starting with the full galaxy simulations, for which I'm not an expert, but I rely on many works that have been published. Simulations that I did myself, as well as other teams, of course, at the kiloparsec box, for kiloparsec box simulations. And then an important question, which really is the most important question of the talk, is really stellar feedback able to regulate star formation? And for my answer, of course, the answer, as you say, is probably no. That's one I will propose. And then I will discuss the star forming cloud simulations, how they compare with the observations. And then, in particular, triggered by these questions of the insufficiency of stellar feedback, I will sort of come back to the classical star formation rate model, so the analytical one, and then stress the limits and propose a more physically motivated one, and compare the predictions with a series of idealized kind of simulations. Okay, and I will try to stress exactly how turbulence behaves and why is it able to reduce the star formation rate. Okay, right. Let's start with simple numbers. If we estimate the amount of stars that you would expect in our galaxy, you would simply divide the amount of molecular gas by the freefall time, and then you would infer something like 100 to 2,000 solar mass per year, but observationally, it's typically 100 times lower values, which is observed. So this means that self-gravity is far too dominant. Star formation is very inefficient. Okay, so this has been around for half a century now, and as I will try to convince you, it's still a puzzle. Then, of course, we have another very important kind of pillar, which is the Schmidt-Kennicott relations. So it states that the number of stars you form per unit of time, expressed here as a column density per unit of time, as a function of column density. So present, of course, some dispersion, but nevertheless, on a remarkably large range of column density, scale with the column density to the 1.4. Of course, there are many discussions on the detail of that. The exponent is still debated. In this more recent paper, they infer something slightly more linear, but on a restricted range. So the exact value of this exponent and the range of the column density that should be used are debated, but nevertheless, broadly speaking, I think it's it's relatively remarkable that over 4 orders of magnitude roughly in current density, you get something which look like a power law with some dispersion. So the origin, of course, of this index is very fundamental. Looking now at, so those measurements here are taken typically at 1 kiloparsec, 1.5 kiloparsec. Okay, more recently, similar types of estimate has been done, but at lower scale. So typically now we are speaking parsec scale, so dense molecular cloud. And in this case, so the same quantities show a steeper exponent, sigma to the 2. And if you look at this quantity here, so something like an efficiency, where you plot the inferred star formation rate divided by the current density and the free fall time, you get something which is relatively flat, so stressing the sigma square dependence, which has some variability, but typically less than a factor 10. It tends to be, there are some outliers, but it's like within a factor 2, 3. Okay. So it's remarkably a constant. Okay. So we have here 2 different scaling that we can try to relate to very simple principles. So having in mind those very simple relation, we can see that, so in particular, the current density is proportional to the density times some thickness. If it's a galaxy, you may think that it's a thickness of this galaxy. So if h is constant, then you immediately combining the things get that the star formation rate, you expect it to be proportional to sigma to the 1.5, which is close to the 1.4. But if collapse occurs, then there is not a single h. It's more that typically you expect the density in a collapsing, in this very simple collapsing model, it's scale like the radius to the -2. Huh? So if you again combine this with the definition of the current density, you expect the current density to vary with the density to the 1/2. And if you plug this in this formula above, you get sigma squared. So very simple explanation. The first, the original Schmidt-Kenniket law has probably to do with star formation rate in a regions that is not globally collapsing, while the second one at small scale is probably typical of a region that is collapsing. Okay, of course it's an interpretation, but I think it makes relative sense. Those are only scaling. And then the question, of course, of the efficiency, the numbers in front, which as we saw are small, of course, is totally a point. And that's a big challenge to estimate or to get physical understanding of those numbers. All right. So let's just have a look in the history. So as I said, it's a big puzzle to explain this low star formation efficiency. And several ideas have been around since the last half century or so. So in the 80s, magnetic field was very popular. So there was this strongly magnetized model. Essentially, the whole molecular clouds were subcritical, meaning that the field was strong enough to counteract gravity. And so the gas had, in a sense, to get rid of the field by the very, slow ambipolar diffusion. So the ions had to drift away, carrying the magnetic field away from the neutral. So that can work, and I will be back to this during the talk. The problem, I don't know if it's a problem, I mean, it's a problem for this theory, that observers tell us that the magnetic field that is being measured seems to be not strong enough, just a measure, okay? Then a bit later, like 20 years later, the paradigm that turbulence may actually do the job and reduce the star formation rate arise. the difficulty with this theory is that if you take a box, turbulent box, if you don't feed the turbulence, it will decay in one constant time. So this means that you have to replenish continuously the energy in some ways. And then, I don't know whether that was later. Yeah, I think it was quantitatively made later. The idea that stellar feedback was responsible of setting a low star formation rate was developed. And this is still, in a sense, undergoing. The difficulty is that there are many types of feedbacks, and this involves high velocities, high temperatures. So numerically, it is challenging. Of course, I would say the most modern version is that the three are linked. Feedback will trigger some turbulence. Turbulence, we would say dynamo, will trigger some magnetic field. Magnetic field will modify the star formation rate, so it will modify the feedback. So at the end of the day, it's probably a combination of the three. And indeed, in the ISM, we know that all energies tends to be comparable, which is a sign that probably these various ingredients are talking to each other. All right. Let's have a look now to the simulations and start from the larger scales and go down to the smaller scales. Before that, just a glimpse of modeling. I guess probably most of you are aware of this. And we solved the radiative, the magneto-hydrodynamical radiative equations. So in our case, we use essentially Ramses. I'm going to present the work of others, which are using slightly different codes, but the principles are the same. Major ingredients here are the treatment of star formation. So essentially, we use the sink particles in our case, which mimic a Lagrangian particle, a star, so it can accrete the gas at some rate and interact gravitationally with it. And then you have to put feedback, and in most studies that I'm going to present here, actually in all studies that I'm going to present here, the resolution is not sufficient to really describe the detail of the star formation. So meaning there is no self-consistent IMF, there is no self-consistent cluster description. So you have to rely on some subgrid model. So typically we assume that the IMF follows the salpeter one. And so each time you form 100 solar mass in the simulation, you know statistically that the massive star should be formed. So you can decide randomly what's the mass of this massive star. You can introduce it in the calculation. And then on this massive star, you can then put the usual feedback. If you know the mass, you know more or less the lifetime, so you can track it. And when the lifetime is over, you have a supernova for most of them. So then you will deliver either momentum, either energy. We have ionizing radiation. So typically, this is treated with the M1 method. So the ionizing radiations is also going to play a role. You have also, of course, to rely on stellar models to know how much flux you have to deliver. You have UV heating, which is warming, say, most of the gas. And when you do small-scale simulation, you also may want to have proto-stellar jets. Okay, so that's the ingredients I'm going to use in the simulations that I'm going to present. Other colleagues have also included stellar winds, cosmic rays. They will all make a factor change, a factor of a few, and they have not been found to be really dominant. Okay. So let's start with a work that have not been associated to. That's a work from Nunes Casinera, Julien Derouillien, and colleagues. So they ran a series of simulations. What I want to stress here is that this is the same run each time, same setup, same everything, except the small-scale modeling for the star formation rates. Okay, so what I want to stress here is that, so you have a Chaos law being assumed, or here you have multi-freefall that I'm going to describe later with some efficiency. And so depending on the choice you are making at a very small scale to prescribe how your star formation occurs, you get very different answers, significantly different answers. But this stage, that's the main message I would like to stress, that this matters if you run a full galaxy simulation.
So can I ask a question? If you don't change, so these are idealized simulations, right?
In which sense
But
idealized?
they're not in a cosmological.
Yes, they are isolated
Very
simulations.
isolated this. So if you don't change the star formation recipe, but just change a little bit the initial conditions, would it not also look quite different?
That's not my work, so I would have to look statistically at what's the results. Perhaps there are people even more expert than me in this type of questions in the literature. I would have to check to answer your questions. Actually, I can answer for smaller scales, which probably behaves a bit similarly. I would say you get some variation. Actually, the work of Sam Jean, for instance, he has been exploring that at the scale of molecular clouds. You get, so you explore different realization and different prescription for the mass of the star that forms. You get the factor like 3 variations on the order of, is it Rebecca you were in this paper? Yeah, okay. So it's probably the case here, but I will have to check. Okay. Yeah.
Just that all of the galaxies look fine to me.
Yeah.
They all look good.
Perhaps.
So what's the problem?
Well, but then you get different answers. So what's the problem is that you would like to know which one is the right one. I mean,
that's different. I mean, the ISM would look very different.
yeah, the ISM is different. Yes.
The standard.
So broadband colors can be okay, but maybe you're saying that some other observations could be in strong conflict with.
I mean, to me, those things seems to be relatively different from each other. So if at the end of the day it's controlled by something that you don't understand, you cannot claim understanding. Okay? So I would say that's the way I would phrase it. And so in terms of Schmidt-Kenniket relation, again, I took a series of work. So in most of this work, they actually use a small scale modeling for the star formation rates. Roughly speaking, I think they are doing relatively well. Of course, they are not able to reproduce, the whole dynamics of the Schmidt-Kenniket relation. Perhaps in these horizon simulations, there are some cases where there is a bit more of coverage, but still it's not those 3 for all of the magnitude. So I think it's encouraging, but A, it's not the full dynamics, and B, it relies on small scale assumptions. So the star formation rate that, as I will show you, is questionable. Okay, now let's go to kiloparsec simulation. So the idea now is that instead of trying to do a full galaxy, you do a small box. So you essentially try to mimic. So this is a tiny part of a galactic disk seen the edge on. So you have some external gravitational field which mimic the stellar gravitational field and the dark matter one. And in this case, the supernova explosions introduce energy. They maintain the turbulence in the galactic disk. So you have 2 equilibrium, one dynamical equilibrium, so gravity against the turbulent dispersion, and one which is energy equilibrium. So you inject energy and you dissipate it by the grid. So many groups have been using this setup. And you can have an idea of what feedback does. Feedback is very important. So those are typically Milky Way type conditions. So the current density is close to the Milky Way one. If there is no feedback, even if there is MHD with some relatively not very strong field, I would say, then you get essentially a catastrophic star formation rate, a bit like the Zuckerman event catastrophe. Everything collapses in 1 free-fall time, essentially. Then when you introduce supernova, and even better, supernova and H2 regions, you reduce the star formation rate by, well, typically at least a factor 10. What's important is the slope. That's the slope you expect from Schmidt-Kennicott. So you are possibly still a bit above, but of course there are numerical error bars, the sync particle, the resolution. So I would say perhaps still a bit too high within a factor 2-3, but probably compatible given the error bars. It's interesting to look at the PDF to understand exactly how this feedback operates. What is really different between these 4 simulations is the diffuse gas. I mean, the gas are around 1 or 10 particles per cc, not the very dense one. There is a little bit more, but overall it's not dominant. That's really in these regions that things are different. So feedbacks just stabilize this diffuse ISM, and most of the mass is actually stored in the diffuse gas, essentially. That's the way it operates. So it prevents the diffuse gas from collapsing all the way.
In here, so the time scale, 160 negatives is just because it's hard to run it longer, or because of the boundary condition cuts down?
Well, you can run it. I mean, you see, you get some kind of relatively stationary regime. Of course, I mean, people can have different opinion in this, but 1 kiloparsec box, the crossing time is not 1 giga-year. So the geometry is very fixed, so you can run it. What stance you would like to give is debatable. I mean, of course, numerically it is possible to do it. Yeah. All right. So in a sense, this is a relative success. Feedback in this case has been able to regulate star formation, bringing the star formation rate to values which are close to the observed one. At least it does much better. Okay. Now comes the problem. Of course, the next step is to vary this current density and try to reproduce the Schmidt-Kennicott. So you do the very same exercise, and then for each current density, you can compute it. And here it failed, okay? In a sense that, so the point, the Milky Way is typically lying here, it was okay, but as you increase the current density, you simply have a star formation rate that is too high. The scaling is not 1.4, okay? It's more like, well, 2.6 in this case. So it's more like the one, it's closer at least to the one that is observed at smaller scale. Like if gravity was just taking over. And this is exactly what's happening, as I will show in a sec. All right. So the question is, what is missing? Or what could we do? And so here what we propose, or what we explore, is that kiloparsec box is not a good model for a galaxy because it's completely isolated, and the galaxy is a much more, of course, dynamical environment. There is probably energy which is generated using a sort of turbulent language injected from the very large scale, like in most systems. Most of the energy usually is at the very large scale. We can think, for example, to the rotation of the galaxy. If by gravity you can tape some energy of this energy, of this, yes, a fraction of this energy, and inject it in the turbulent cascade, then you have a very important source of energy. Okay, so that's what we are having in mind. It's actually an idea that is not completely new. It has been proposed by Bono and also by Krumholz. And so what we do to mimic this is that we drive the turbulence. So we add the turbulence driving in those boxes in in 2D only, because you don't expect to have much energy injection in the vertical direction. So we use this Hochstein-Leuenbeck process, which has been proposed by Schmidt et al. Okay, and then essentially we drive up to the point where we can satisfy the star formation rate, I mean the Schmidt-Kennicotte relation. Well, I would like to note in passing that if you do some elementary scaling, so computing, this epsilon, the energy, the turbulent rate, if you assume that your 2 parameter is on the order of 1, then you find that the energy, the power of the energy that you should inject to match this should go like sigma to the 4, okay? And I think that's essentially the problem, that the amount of energy that is available through feedback scale with the star formation rate, which is 1.4. Okay, so as you crank up your current density, there is just not enough energy with feedback to counteract gravity, because it does not increase sufficiently rapidly with current density. Okay. All right, so let's look at what it does. So first, without driving, that's 6. That's a current density 6 times the Milky Way one. You have of course stellar feedback there, and yeah. So what you see is there is this enormous sort of complex that is globally collapsing, and there is just a huge amount of star formation rate going on. There is nothing to prevent this structure from collapsing because it's very dense. Okay. If you have some driving, you see very rapidly a completely different story. That the structures, the large-scale structures, cannot collapse because they are sheared apart by the turbulence. Of course, it has to be strong enough, and that's very deep, or the very profound questions that we are trying to tackle. But you see a completely different picture. Okay, you just shear apart your complexes, and you reduce significantly the star formation rate.
Is this in the? Are we looking down on the plane?
Yeah. You're looking on top of the plane. Sorry.
It's still in a shearing box.
We don't have shear here. I mean, actually, shear have been explored in this paper. There was shear actually. The shear does not do very much. It reduced perhaps by a factor 2-ish, but the shear at the galaxy at the kiloparsec level is not very strong. It does not change very much the star formation rate, particularly when you increase the density. Okay, so that's the Schmidt-Kennicotte relations we obtained. So this is without without turbulent driving. So you get a star formation rate that is orders of magnitudes larger than the Schmidt-Kennicotte relation. And if you drive strong enough the turbulence, then you can reduce it and bring it to the offset value. All right. Of course, at this stage, it's not fully self-consistent because we rely on this driving, and so the whole question is this driving realistic? And that's the whole point. If we compare feedback and the externally driven turbulence that is needed for Milky Way type, so this is the supernova, the star formation rate where we have both the driving and the stellar feedback. This is what you get if there is only a driving, and this is what you get if there is only feedback. So you see that feedback is actually doing most of the work, is the one that is most efficiently reduced in the star formation rate, as in the very first simulation I was showing you, where it was almost okay in terms of star formation rate. If you go to galaxy which is 4 or 5 times denser than the Milky Way, that's the contrary. Okay, feedback, as you see, fail to significantly reduce the star formation rate, and it's essentially most of the job is done by the driving. Of course, it's much better if you have a combination of the two, and that's probably the way it should be. It should really operate. So it's a combination of stellar feedback and driving in this case. Right. So far, that's the result we found being summarized here. That's without driving, that's with driving. I would like to stress that another team has been finding very similar results, the team of Kim and Ostraker. That's their point, actually, okay? Where they essentially follow, they don't have driving, and they have only stellar feedback, and they find trends which appears to us very similar to what we have. Another team has been publishing different results. That's very interesting, I think, it's very fundamental to compare the results of different teams. Okay, this is Rajan et al. 2023 with Torsten Nab. So they get a good agreement, so not with the same data. So we are using here the data by Kinnickett and Evans, and they use the data by Lowa et al., which are a bit higher, like a factor 2-3. But still, their star formation rates are lower than us by a factor 3, roughly. So there are two important remarks. First, as we see from this curve here, I think they have the same trends than we do. If they would go to higher time density, they would exactly face the same problem that we do. That's just from their data. The slope they get is actually 2.1. It's not 2. And second, looking at the details, they actually have a higher magnetization. So coming back to the magnetic field, we also have explored the influence of the magnetic field as another possible solution of that problem. So that's what is described here. This is the star formation rate as a function of magnetic field for different column densities. So in particular, if I focus on this one, again, 6 times larger than the Milky Way, you find, as you would expect, that magnetic field has a very strong impact. And actually, the magnetization for this run is about there. Okay, so my best guess is that the results are actually close to ours. It's just that they have been using a stronger field. I'm not claiming that they should not have used a stronger field because the level of knowledge of magnetic field on other galaxies is not great, I would say. So this is a viable solution, perhaps. Can be turbulence, it can be magnetic field, it can be the combination of the two. In any case, my impression, or more than my impression, that my conclusion is that if you don't have one of those two ingredients, feedback in itself, at least in the kiloparsec box context, seems to not being able to make the job in explaining the Schmidt-Kennickett relation. Yes?
Can you explain how the magnetic field inhibits the star formation in this scenario?
Oh, yeah, it's the magnetic pressure, essentially. Yeah, essentially. There would be some similarities with the second part of the talk, where you would have to replace turbulence support by magnetic support, essentially. But yes, essentially, you crank up when you have a support, okay, like magnetic field or turbulence, you define a new Jeans mass. So it should be the turbulent Jeans mass or the magnetic Jeans mass. So you, in order to be unstable, you need to pick up a larger piece of gas, okay? And when this piece of gas reaches the size of the system, then you start lacking sufficient fluctuations to generate instability. And that's the essence of it.
The simulations of Torsten, the feedback model that they're using is similar.
They have cosmic rays. Actually, this point here has cosmic rays. This has not. This one has cosmic ray. This has not. But so the cosmic ray does a little bit. I think they also have stellar wind that we don't have. But stellar wind and supernova, at the end of the day, it's very similar type of.
So it's not a strong thing. It's not significant to explain the difference.
I don't think so, because I think all team agree that supernova and H2 regions are doing a lot of the work. Then you have subtleties. Actually, Sanjin, for instance, has been studying in detail the interaction with the wind and the H2 regions. And sometimes you can have nasty things with the wind actually being trapped in the H2 regions. And so those are small scale issues that we cannot discuss with such coarse resolution, and they can make probably difference by a factor of the few. But as far as I can tell, the conclusions that supernova and H2 regions are doing most of the work seems to be robust. Okay. Then coming back a sec on the energy issue, which of course is quite important. For us, the whole question is where does this energy comes from? Okay, because we are okay, and so that's comparisons with energy that is available for supernova, and that's from rotation with an efficiency that goes between 0.1 and 1. And that's what we would require to sustain this turbulence that we are driving. So the various points corresponds to various values of the magnetic field. So yeah, it seems that using most of the energy we could sustain up to a current density approaching, say, 100 solar mass per ±2. But if you remind the scaling of the Schmidt-Kenniket relation extend far over this. So here I don't know. Okay, that's my honest answer. So certainly more work has to be done to verify or falsify this scenario. I think we need to understand exactly what's going on with the star formation, with the injection of turbulence, and also with the dynamo, to see if a strong field can be generated, with increasing current density. I think that's all open. Yeah.
One question about the turbulence part.
Sorry.
So your turbulence part in the next, before, like just the slide you showed before. So Christoph Frommer is arguing for a while that like the shear between the hot corona around the galaxy plus like the rotating galaxy also introduces some sort of turbulence.
Yes.
But that is not included in your turbulence term.
Our turbulence is a very simple minor thing. It's just a driving. There is no attempt to do physical model. Just a driving.
Yeah.
To do what you describe, you need to do probably a full galaxy simulation. And then the difficulty is that you don't describe very well the small scale, or it's extremely expensive, so you cannot run many models. So that's the difficulty. That's why we have to play around with scale. Of course, scale have their advantage and their disadvantage, and you want to combine them in the most clever way to take care of the bias. Yeah.
A question along this line. I was wondering if larger scale simulation, like cosmological simulation, I guess they kind of place some constraint on the energy injection, for instance, from region feedback or from minor mergers from galaxies. I was wondering if these kind of physical processes could inject energy.
No, yeah, probably. I think that's certainly a very important step, is to make a detailed energy balance of the energy in those large scales. I mean, one should remind something important from the very basic knowledge of turbulence. If you do this experiment, where you take two rotating cylinders, we know that there is a critical Reynolds number, which is typically around a few hundred, depending on your system. If you are below this number, your flow is completely laminar, and if you are above it, it becomes turbulence. The Reynolds number in galaxy simulation, I don't think is very large, just because of resolution. So I think that's an important question to address. I'm not saying that the answer is this. I'm just saying that there is a possibility, just from elementary, physical consideration, that the simulation actually are missing the turbulent cascade because they are too viscous. And that's not the dense regions. That's really the bulk. Okay. So right. So I wanted now to quickly discuss the the star-forming cloud simulations. If you remember, the Schmidt-Kennicut relation is not the same at kiloparsec scale and at cloud scale. So here I'm using a simulation we published in the group by Antoine Verliard, where we do a clump calculations. So these simulations, so it's a 10 to the 4 solar mass star-forming clumps. So we have jets and H2 regions. So supernova are not relevant here because there is no time for supernova to explode. And so we vary, no feedback, jets, H2 regions, or a jet and H2 regions. So that's the typical sync mass as a function of time. So you see that that's when there is no feedback, the star formation rate is again high, and when you have those feedback, you reduce it.
Sorry, so what feedback are you talking about, given that you don't have supernova explosion?
It's H2 regions and jets, protostellar jets.
Okay.
Okay.
So that's stellar winds? Or...
No, jets, protostellar jets, that the one which are launched by the magneto-centrifugal process. So you have rotating field lines. It's launched really at the scale of the protostar, and so the velocity is typically the gravitational infall velocity, and the amount of mass that is being ejected is typically 10% of the accreted mass. So that's
like a small version of an AGN.
Yes, or AGN are a bigger version of that because they've been discovered first. Sorry, I'm right. Okay, so it's not a joke. Okay, right. So we use those simulations, and that's a paper published recently by Paolo Swin, doing his thesis with Annie Davagno in Marseille. So what Paolo did is reproduce essentially the observational procedure that Pocrel et al. has been developing. So they have contours, and they count the number of sink, and they divide the number of sink by the mass of the gas that is available. So they so in this paper we reproduce nicely the sigma square dependence. Okay, and there is a first. So that's the Pocrel et al. Data, and that's the efficiency defined by this relation. So as you see, if you have purely gravity, you are off by a fair amount. If you are feedback, you do much better work. You are still a bit off by a factor 2 to 3. It turns out that Paolo has identified several bias. In particular, the dominant one is the extinction one, that he believes that many stars actually are missed because of the high extinction. And when he take this into account, he obtained much better agreement between the data, the observational data, and the numerical data. So for now, I would say that at small scale, the combination of gravity and feedback, as far as I can tell, is able to make the job. Okay, so for me, the problem that we have now to face is the fact that at kiloparsec scale, feedback does not seem to make to provide sufficient support for the high current density galaxy. For Milky Way, it's okay. All right. So this drive important questions. So the first one is, what could be the source of this turbulence? I tried to give ideas, but this is, as has been stressed by the question, the large-scale questions that I'm not able to address with the simulation. Then the second question is how exactly turbulence managed to reduce the star formation rate. So that was the Joachim question for the magnetic field, but I think there's some similarity. And can we provide a model, analytical model, that could take this into account and that could be used on large-scale simulations? All right. So first, let me introduce the classical star formation rate model. So that's the physical ingredient they are using. So it's a series of paper since like 20 years or so. So the idea is that you rely on the log normal PDF, which is the density probability function for that is generated by turbulence, which is represented there from this paper here. And essentially the width of this PDF has been found to increase with the Mach number. The larger, or the more intensively you dry, the broader this PDF because you generate shocks and so on. Then the second ingredient which has been used is the sonic length. So the idea is that at some stage the turbulence, the velocity dispersion become comparable to the sound speed. It's called the sonic length. And people have been proposing that you will use this sonic length to define, to calculate a critical Jeans length, and so a critical density over which your gas is unstable. And so to get the star formation rate, you essentially integrate this part of the PDF. Okay, so you determine this critical density, and then you sum over the PDF. And of course, you have to divide by some times, which is taken to be the free fall time, right? And so you obtain this expression. Some comparisons have been done with star formation clump observations, also with simulations. They seem to be doing a reasonable job, except perhaps if you look at here, so that's the VL parameter. So as you go to higher VL, you are higher Mach, you start seeing the deviations here, okay? But for the low sort of Mach number, seems to be doing reasonably well. Okay, so why do we worry? Well, I think there are several inconsistencies in this approach. First is, why do we use the free fall time? The PDF that is used comes from turbulence. Okay, so if you take a free fall time, okay, of course, the piece of fluid that you have here disappear in one free fall time. So if you are interested by the star formation rate over a free fall time, that's fine. But if you are interested by the stationary free fall rate, you have this piece of fluid to be replenished. Otherwise, you run out of matter. So it means that you have to worry about the replenishment of your gas. And because your PDF is actually a turbulent one, this time must come from turbulence, not from gravity. Okay, so you must have somehow a turbulent replenishment time, which is the time you need to rejuvenate your dense gas. Second, why a density threshold? As I just described, there is this critical density threshold. But there is no reason why the sonic length should be important in this game. Even if you have a turbulent piece of fluid, if density is strong enough, still it will collapse. So sonic length is not playing a major role there. So turbulence support should be accounted for. I mean, if you take a piece of fluid and if you check it sufficiently strongly, your piece of fluid explodes. So that's turbulence support. And then finally, the PDF is a one-point function. You can take very different flows with exactly the same density PDF, but with completely different statistical properties. You can have a big blob, or you can have, you can take your big blob and spread it in many small ones. Each of the small blob could be gravitationally stable because they are small. And so for the same PDF, you can completely stabilize your flow. So that information should be included there as well. All right, so I'm just going to give a glimpse of this model. So the idea is based on the so-called the press injector type of formalisms that we have been also using to compute predict model for the initial mass function. So the idea is that you can estimate the mass at a scale R, so the unstable mass at scale R, by defining a scale-dependent density threshold. Delta is the log of the density, and summing over the scale-dependent PDF. So that gives you a mass at scale R, which should be independent. And this mass goes in your star, in your gravitational collapse object. So those two masses are equal by definition. From the analysis, you can compute the critical mass that is unstable. Okay, this is essentially virial. You have thermal support and you have turbulent support. It's scale dependent. from this mass, you just divide by the volume, then you get a delta quit, which is scale dependent, okay? And because you have the scale dependence here, you can derive this equality here with respect to the scale, and you get a prediction for the mass spectrum of the gravitationally unstable structure, the clamps. Okay, so now you know how your clamps are distributed, and there is some spatial informations for the statistics of the flow through the density PDF. In particular, its variance depends on the power spectrum of the log of the density. So the spatial distribution is encoded in the PDF. Okay. So you have turbulence support, and here's spatial distribution. And so now you have to divide by some time that I'm going to discuss next slide, which is the replenishment time. And so now you sum over this mass spectrum divided by the local replenishment time, and you get a star formation rate. Okay. Right. So the replenishment time is really a local turbulence one. So you combine different expressions. So you have the crossing time, which is the local scale divided by the velocity dispersion, the velocity dispersion dependence, that's from turbulence. And then you assume that everything is 1D. So which means that as you compress a scale from air to air prime, it's essentially a shock. So it's a 1D compression. So the density goes with the radius according to this relation here. Okay, so from this you can compute further this time here and get an expressions which involve the scale air and the density. That's the expression of your local crossing time. And then you have to weight it by the density PDF because, of course, depending on the different density distributions, you will get distribution of replenishment time. So you have to weight it to get the mean value. So that's what is done here essentially. So that's the way, that's the time we used for this to estimate how fast a turbulence replenished the gas. And we actually verify from the, it's hard to compute exactly this time, but what we did the following experiment. We took turbulent box and we suppresses all the dense gas, okay? And then we measure how much time it takes to actually replenish the dense gas in this simulation. And so you see from this curve here that it takes actually several crossing time to replenish the dense gas, which means that thinking that the dense gas is a small scale issue is not the right way to think. The dense gas is the consequence of the compression of the large scales. You have dense gas, extremely dense gas, because you have compressed like crazy the gas that was sitting at very large scale. So it's a large scale quantity at the end of the day.
The reflection in the test is done by turbulence.
Yes, yes.
Isothermal
turbulence, yes. And so here you have the comparisons between the free fall time and the replenishment time. So the free fall time is typically the dashed line. So you see that the free fall time is much shorter than the replenishment time, which is what I was trying to describe previously. So of course, this will have consequences on the star formation rate, because if you use the free fall time, then you get much higher star formation rate, but you cannot sustain them. So again, it's a matter of time scale. If you set a dense cloud and you want to measure it for a short time, that's completely fine. That's what should be done. But if you want to average it over a longer period, that's not fine. All right. So let's look at the prediction of this model. So that's the star formation rate as a function of Mach number. So as you see, at low Mach number, the star formation rate is relatively smooth. It's actually close. I will come back more quantitatively in a sec with the other model I was just showing, the former version. You start having strong deviations at some Mach number, okay? And you see here you have a very severe drop in the star formation rate. And that drops depends on the detail of the mass spectrum of the log of the density. Sorry, of the power spectrum of the log of the density. So depending on which index you pick, you get different curves here. So if your power spectrum is like very shallow, then you get much stiffer behavior. So physically, what's happened is that as you crank up the Mach number, you essentially stabilize part of the flow that were previously stable. So loosely speaking, you replace a thermal Jeans mass by a turbulent Jeans mass. So as the Mach number increase, you increase the size of the piece of gas you must use to have collapse. But at some stage, that size becomes comparable with, in your case, the injection length, so at which you inject turbulence. For the case of a galaxy, this could be the thickness of the galaxy. And in this case, there are no fluctuations which is present in your system for it to be unstable. So it becomes much more difficult to have a seed for gravitational collapse. And that's the origin of this drop. And that's why, that's the main difference with former models, okay? All right, so
For the Costain-Hopkins one, it's just like the density distribution that you.
okay, there is another subtlety that I, in the interest of time, I didn't want to go through, but if you force me, I will happily do it. There is actually another important ingredient there, which is the PDF itself. So most studies so far have been using the log normal PDF, and comparisons with simulations reveal that what I call the Castan-Hopkins PDF, which is inherited from the work of Castan and then sort of used by Phil Hopkins to do a series of fits from many simulations. It's doing a much better work. It's actually a log normal Poisson process with, I mean, very close from the intermittent models which have been developed in turbulence by, for instance, Che and Lebesgue. And as you see, at low Mach, again, they are very close, but at high Mach, they are very different.
Yeah.
And you see that the log normal produce much more dense gas than this PDF.
Also, that's why you get a larger suppression.
Yes. So, and as you see, that's comparisons between what we call the turbulent support model and the classical Padua Northwood. So they behave very differently for the log normal already, but if you take the Hopkins, it's even worse. I mean, these models, essentially there is no dense gas, not enough dense gas, and you would predict the star formation rate is almost zero because the model, I mean, the star formation rate here relies on the dense part, which are completely gone if you use this PDF.
Okay.
So that's another, well, I mean, in the turbulent support model, because there is much less emphasis put on the dense gas itself, because we integrate over the full distribution, the effect is considerably less. There are some effects, but it's much less, as you can see from this plot. Okay. So, of course, we want to test this model. And first, so we run first simulation without gravity. We measure statistics like the PDF. We measure the power spectrum of the log of the density as a function of Mach number. And then we run the simulation with self-gravity, and we infer a star formation rate, and then we compare the star formation rate in the model and in the simulation. So that's what is found from the simulation. That's for different driving. That's purely compressible. That's purely compressible. That's purely solenoidal, and that's mixed. So you see a behavior from the simulations where you have some mild dependence on the, I mean, almost no dependence on the Mach number up to that value, and then you get a decrease. And that's a comparison with the classical model. You see that in these regions, so we use, to answer your question, we use the log normal, the Castan-Hopkins here. You see measure deviations from the simulations in the high Mach number. So the low Mach number is kind of okay, as has been found from previous set of simulation, of course, but not when you go at high Mach number. It's a bit better if you use the log normal, but as I said, the log normal, we don't see it in the simulation. So, okay. And that's the comparisons between the turbulent support model and simulation. So it's not perfect, but it's much better. I think in particular, we captured a drop here. Looking, I mean, having played with that in details, you actually need a lot of information, of detailed information of your flow to predict the star formation rate. You really need to, to get detailed power spectrum. You need to get a detailed PDF. So prediction is in case is even a bit. I mean, you have to assume if you want to use it that the statistics you have been measuring in those simulations are the one that are also developing in your own system. So it's not an easy business. At the end of the day, it really depends on the detail of the flow. I mean, if you want to get accurate values. All right. Okay, so I think it's doing much better. I think we can probably do even. I mean, it's, as I said, it's not perfect. So I think there is room for improvement, and that's for sure. But yeah, I think it's already a significant improvement. So this. Just before I finish, I wanted to do a small advertisement about the Galactica database, which is a concept that we developed and where you can broadcast essentially your numerical simulation. If some of you are interested by this, please come back to me and I will give you some detail. Okay, with this, I finish my talk. So my most important message is that to me, there are strong evidence now that the feedback is not sufficient to regulate star formation, at least at the kiloparsec type of scales. It's okay at a much smaller scale, but then what we are witnessing is global collapse with ARG. So the classical SFR models, I think, suffer, needs improvement. The turbulent support model provides some improvement. And whatever the final answer would be, I think the star formation rate, it's fair to say, it's a consequence of the full turbulence magnetic field and stellar feedback. Thank you for your attention.
Thanks for the nice talk. One thing you didn't discuss, and maybe it's not important, what's the role of the central black hole in active or non-active galaxy?
I haven't been touching on that at all. Yeah, at the moment, I'm concentrating on the Milky Way and Delta Galaxy, but I didn't touch on that.
But do you have any general comment based on other works?
I'm not an expert in this field. I think from my basic level of understanding, and I listen to experts in the field, I think the question of whether the central black hole is important for the galaxy or not is still unsettled. There are very different opinions. So I'm not more expert than those people, so I cannot say.
Questions? Yes.
I have a very nice one. Thanks for the talk. Looking at the movies that you showed, the difference between the without driving and driving, I was wondering why the transformation region is located somewhere else in the bottom panel. Is it an effect of the initial conditions, or?
Oh no, it's because turbulence has shuffled the gas around very significantly. You can see this, of course, there is the initial phase, but after sometimes you see the turbulence developing and the fields look completely different because the target turbulence is very significant and just redistribute the gas completely.
Yeah, the question on that. So the turbulence support model you described again. So in that model, the replanetary The reality will also, it's still related to the larger scale, right? Because you have condition, whatever but then, what I missed is you showed how to calculate the reflected time in the model, right? But then you need some boundary condition. You know, if you apply that to, you know, to explain what you see, right?
This is always the injection length, which is fundamental. When you have turbulence, you have to specify the injection
Okay,
length.
so that's where the boundary. Yeah.
And that would be the boundary conditions,
Okay.
and which is a complicated one because if you have a galaxy, is it the thickness or is it the bigger scale? It's not an easy one.
Okay.
So, yeah.
I have one inane cultural question. And why now is Schmidt before Kennicott
Oh,
written? I don't know if you know.
uh,
It came up a few times, and I learned this when I was a young lad in school that
it was a Kennicott Schmidt.
Schmidt came first.
Well, Schmidt is 69 and Kennicott is 80 something. So
The original is.
Chronologically speaking, it's always the next way.
Okay, well, I don't know, this,
No, it's a good point, yeah.
yeah.
But then it's looking at the limit of the law, not the
I wanted to ask about, can you comment on the, like, this observational confirmation of this model based on future observations or current observation? Like, is there a way to kind of constrain star formation rate in Milky Way like galaxy or Milky Way itself using observation?
My impression is that, well, I'm not an observer, but the recent Fung survey, for instance, did you know, quite a good job, and they found, you know, results that were similar, broadly speaking, to what has been perhaps not computed by Schmidt, but later by Kennicott. Yeah, my impression is that there are, perhaps we should know better, in my opinion, what happened on the very high current density galaxies. And when I discussed with my colleagues, observer colleagues, because I would like to have more information as a theorist, I would like to know the size of the galaxy, the thickness, and so on. And they have difficulties to answer because of the observational techniques. So to me, this is an important aspect to clarify. We need to get more than just the current density. We need to get more information. We need to have the size of the system, the thickness. If we want to confirm or again to falsify, I don't know, this proposition that turbulence or perhaps magnetic field or perhaps a combination of the two is responsible at the end of the day for setting the low star formation rate, you know, we need to have a much more detailed knowledge on the systems and how they are connected to the large scales.
But what about the power law in the small scale versus large scale? That is also.
You mean these things?
Yeah.
Yeah, here it's a bit newer. I think it will be, well, the first paper were like more than 10 years ago. But yeah, I think it would be nice to extend the observation and perhaps also to try to make a connection between the kiloparsec scales and those scales to see how how the transition. I think that would be great. Because my best interpretation of these two behavior, as I said, is that we are witnessing in one case a collapsing structure, not in the other case. So that's very fundamental in a sense.
Yeah. Thank you.
So we thank a lot again.
Interesting stuff on this new model that you were showing. No, the turbulence.
So in the high, I actually 60% formation seems